ones. All right, so we know that continuity is tied in with limits. And what we have here is a function that's not defined at 0, 0. So it looks like your domain could be all real numbers except for 0, 0. If this was just a function. I guess we don't need a set notation here. Sorry. So this is saying all real numbers except for 0, 0. But if they go on and define the limit to be equal to 0 there, then it's possible that this could be a completely nice continuous function. So if the limit as xy approaches 0, 0 of this function, and by this function I mean this whole piecewise function, exists and is actually equal to whatever they say it should equal to, then it would be continuous. On not only the domain of the original function, but the whole thing, including 0, 0. So this would be, I don't know, in pre-calculus or calculus, maybe you guys studied the idea of a removable discontinuity, where it looks like it's a nice graph, except there's a hole in the graph. And so can we just put one point on this graph to make it continuous? And usually the idea of, I guess I should have checked this out first because I want to make sure that this actually would work. But the idea is that for these problems here, you know, we did a problem yesterday where we took two different paths, and then we found that in those two different paths, we got it to not equal each other. So your friend was was up on the ridge, and you're down in a little valley, and then you're trying to meet up at 0, 0, and then your friend was up at height 1 and your height -1, and so you guys didn't meet, except if you went through that little hole in the middle, and you know that whole story we had. So so if your limit doesn't exist, then it's not going to be continuous regardless of what point you try to put in there. So that's what we're looking for to see if it's not continuous. So proving that something's not continuous is easier than proving that something is continuous. Because if you're trying to prove something is continuous, you'd have to try, you know, 1 path, 2 paths, 3 paths, 4. You have to try an infinite number of paths. Because at 0, 0, there's an infinite number of ways to get there. You can get there through a straight line. So already straight lines going to 0, 0, there's an infinite number of them. You can go there via a curve. And there are some paths where if you go in the curve, then it's not going to give you the same limit as going a different way. If they all equal each other, then you're kind of stuck. That means it's not going to be easy to find a path. So to show that something does have a limit, you have to be a lot more precise and use what they have called epsilons and deltas, where you get closer and closer and stuff. But we're not going to go there. If you're a math major, then you probably should look it up. Actually, speaking of math people, I think they're going to have a math club going on. Anybody know anything about that? Yeah. Oh, so when is it?
I think it's like
Thursday, 2:30. Yeah, so Thursday, 2:30 to 3:30 at the STEM Center. If you're a math major interested in math, you can go check it out and see what they talk about. All right, so what I'm going to do is I'm going to try a couple of paths to get to the origin to see if this thing has a limit, and hopefully it doesn't, so that we can be done with this. And if all the paths that I try, you end up with the same limit, 0, 0, then we might be stuck. Okay, so let's see. Let's try. Let's try x equals 0. So coming along the y-axis, right? So let's take a look at this function. This is the function that we're focused on. When x is equal to 0, we're taking the limit as, I'll write this one time, and then I don't want to, and then I'll write the shortcut. We're going to be looking at the limit as x, y goes to 0, 0 of this function. Using different paths. So I'll write that function here once, and then now whenever we try a path, I'll just substitute the variable that we need to substitute. So as x goes to 0, I have the limit as x is already 0 down below, so y is the only variable left going to 0. And then we have 0 on top. 0 plus 0 plus this is important that the denominator is non-zero, so we have a y squared there. I mean, eventually we'll push it to 0, but before we even take the limit, this whole thing is already 0. So if you try to take a path along the y-axis, you're going to be approaching 0, which is what they have there. Okay, so that's a good sign that it might be continuous. Yeah. No, because y, we didn't say y is equal to 0. Y is going to approach 0, but we're saying that y is not equal to 0 yet. And the thing is, before we even take the limit, this whole fraction already goes to 0, is equal to 0. Okay, that's really subtle. That idea that with the limits, before you take the limit, it's already equal to 0, and so the whole thing is going to be equal to 0. Versus taking the limit and then it's going to go to 0. So those two things are a little bit different. And here, it's going to be 0 before we even take the limit. In fact, if you want, maybe we can say we're taking the limit as y approaches 0, and then we simplify this fraction and we get 0 there already. So we're really taking the limit as y goes to 0 of 0, which is 0. Yeah. So now let's try the other side. Y is equal to 0. We'll take the limit, and then I'm looking at this box again that I prepared. So y is equal to 0 all the way through, and so the only variable I have left is x. And x is still going to go to 0. So x times 0 is 0 in the numerator, and this time my x squared is going to stay there. It's not 0 yet until we take the limit. And then I have a couple of other zeros there. So we're going to take the limit as x approaches 0 of 0, which is equal to 0. Okay, well, looks weird. So it looks like it's 0, right? But remember, these are only two paths. Technically, it's four paths. It's coming from the left and coming from the right, and then coming from the top, coming from the bottom. So there's technically four of these that we've taken care of. But remember, there's an infinite number of them, so we got an infinite number more to go. And hopefully one of them will give us a different number, and then we'd be done. And if we go do this an infinite number of times, it all is equal to 0, then it must be equal to 0. So let's try another one. How about the diagonal path? Y is equal to x. So if y is equal to x, I'll just choose 1. I'll just choose x to stay alive, and then y is equal to x. So they're both going to be 0. And then I have x times x. X times x. And I have x squared. And then x times x again. And y squared. But y is equal to x, so this is another x squared. Okay, now again, before we take the limit, we simplify. And we have x squared, and then we have 3x squared. Is that right? And then it looks like even before we take the limit, we can cancel the x squareds. There we go, 1/3. Not equal to 0. So now we've found a path that doesn't bring us to the same number as the other two paths, the other four paths that we took. So that must mean the limit doesn't exist, because we found another path that went in a different way. So limit DNE does not exist. And if the limit doesn't exist, then it's not going to be continuous there. So, this is a so, not a go. Not continuous. So it turns out that it's continuous everywhere else because the function's continuous everywhere else except for 0. And what they tried to do is they tried to patch it up with a 0 in the piecewise function by putting the 0 here. They try to say, hey, what if I just put 0 there? Now is it going to be continuous? Well, we found that the limit doesn't exist there, so if the limit doesn't exist, then it's not going to be continuous there. Regardless of one patch number that you give, it's not going to work. So, it'll be continuous everywhere. So this will stay its domain. So it looks like it's continuous everywhere except for 0, and this is probably the best set notation that describes it. We can have positive and negative numbers. Here it says only positive. Here it says all x real numbers and all the y's except y doesn't equal to 0, so they eliminate the x-axis there. That's not it. So it works for everything. And here it's all real numbers. It's not that. And here it's the product is equal to 0 or is not equal to 0. Yeah, this is an interesting game. Maybe we should try to figure out what these sets are actually saying. Let me take a copy of these sets, and then we'll take a look at trying to graph their domain. I think that's more mathematical instead of, mathematical as in for math majors. But for now, are there any questions about this conclusion that we came up with? Yeah?
So, how do you prove the limit doesn't exist? Using that way, you have to show every path.
Right. So you're obviously not going to show the infinite number of paths, and so the only way to do this at this point, at this level, is to use epsilon deltas. So that is, do you know the epsilon delta definition of a limit? Do you really want to know? define useful. So here's how they do it in math when I was back in the day. We use symbols in math. And here's a shortcut. Upside down A says for all. And this is your symbol for epsilon. And we want epsilon to be positive. For all epsilon bigger than 0, this is a symbol for there exists a delta bigger than 0. And this is a shorthand symbol for such that. For all epsilon bigger than 0, there exists a delta such that. I guess I was going to say if then, but instead of an if then, we can just do an implication. So if, and I won't write the if, I guess the 0 here doesn't matter. Delta, oh, we're talking about distance. So we're talking about a distance from some point and some limit. So such that, how's it go? F of x, y minus L is less than epsilon. Uh-oh, I'm blanking out. Is this, if, oh, this comes at the end, sorry. So it's the magnitude of delta with the xy. So there's probably a neater way to write this. So the magnitude of the vector between the point that you're approaching to, like 0, 0, and some random point xy is less than delta, then, and this arrow here says implies. So this is like an if this, then this is the conclusion. So this is your official definition. And what that says, let's see if we can draw a picture. So this is x naught, y naught, and this is your surface. Z is equal to f of xy. So what they're saying is that if I give you a small epsilon, and epsilon is a positive distance. Can you see that? Epsilon. Some positive distance, and we generally want to make it small. Then you should be able to find a radius, a distance, a positive distance, so that if I make a little radius circle, a net, a circle, a disk, then every value that goes into the function is going to give me a height that is going to be within epsilon of your limit. And so doing the algebra for these things get really complicated. Doing the algebra for an epsilon delta proof in Calc 1 can get complicated unless you're talking about a line or something. And then there's proofs. There's ways to prove these things that they call bounding. You're supposed to try to bound something. Anyways, let's just say this is the definition, and I don't know if they have this definition in the book, the epsilon delta, but if they were, I have the book open.
What was that?
Oh, if the limit exists and the point exists at that point, or the z value exists at that point, then it's continuous. Yeah, they have this. So they have this definition here, which is similar to the definition that I wrote up. And it's the same idea. It's saying the same thing. And so this works for Rn, and the example that I gave is for R2. All right. So we're going to not really deal with this stuff. So if I was going to give you a problem on the quiz or on an exam, I wouldn't give you a problem where the limit does exist. I'll give you a problem where the limit does not exist, and it'll be up to you to find the paths that will give you the different limits, the different answers. Okay? All right, so, yeah.
Is there a good technique for choosing the first? Just try to easy stuff first.
Well, let me show you.
Try setting various.
Yeah, let me show you my thinking on the one that we just did. So I see an x, y up on top, and then I see sum and difference down in the bottom. So immediately I know 0, either x or y equal to 0 is going to give me the same result. So because I knew that, I probably didn't need to do these two different things. I could have just tried one of them, and I know the other one's going to be the same answer. So the next thing I would look at is that, okay, now how are the numerator and denominators related? So there's an x squared and a y squared, okay, and this is x and y. So if I set them equal to each other, then it looks like there's going to be an x squared, and an x squared. So already I know that the denominator is going to have an x squared, the numerator is going to have an x squared, and I can cancel that out. So there are other not tricky, but there's other problems where the y would be squared on top. And so if that's squared, then you might have to take a different path to get there. And I think this is y squared, and I think this might be y to the fourth or something. There are other combinations where the path to take would be the x is equal to y squared graph or something, a parabola. Pardon me? Yeah, I mean, you're the one doing the path, and what you want to do is you want to get a path that's going to give you a different answer when you're doing the limits. So part of that is being comfortable with the limits, and then the other part, the harder part now, I say you're comfortable with the limits because you guys have done limits in pre-calculus and in calculus. But now the tricky part is looking at these powers and seeing how they might relate to give you a different result, which is what you want, right? You want two different results. Okay? All right. So limits and continuity kind of go together. And so I wanted to take a look at these interesting sets that they gave here, and we'll keep it on this page. I'll just say this is kind of like a mathy page. And let's try to figure out what these sets look like. So this one is all real numbers. Let me just say R. So there's not much to talk about there. This one is going to be all real numbers except for 0, 0, which is what our result was, all real numbers, and then a hole right here. Maybe I'll make that bigger. So this one is all real numbers except for that hole. All right, now let's see. What does this one look like? X is bigger than 0, y is bigger than 0. First quadrant, do we include the axes? So not including the axes. So maybe I'll draw a dotted line. So it's the first quadrant, not including the axis. Does that make sense? How to read that? This one looks pretty interesting too. What's missing? The what? The x-axis, right? So this one would be everything above and everything below, and not including the x-axis. That's when y is equal to 0, right? And y cannot equal to 0. Can you give me a function that would have this domain? No, just make one up with functions. X over y. Y cannot be equal to 0. X can be anything. And y, aside from not being equal to 0, can be anything. So this will work, right? You see that? How about this one? This one, I guess, would be interesting also. How would this one look like? What? So the only time x times y is going to be equal to 0 is if one of x or y is equal to 0, right? So everywhere except for when x is y equals 0. Okay? Yeah, and then you could try to come up with a function that would have this as its domain. That would be, hey, that's an interesting exercise. Sounds like a good quiz question. Maybe not. All right. Anyways, I think we need to move on. So we're going to move on to the next section. Oh, yeah, I was going to do one of those. Dang. Yeah, I know, I saw it. Where is it? I did see it. Oh, this one. So here's another one of those. We're going to first put in the values for x, y, and z, 0, 0, 0. If we do that, we'll see that everything is going to be 0 on top and 0 on the bottom. So we don't know if this does exist or not based on just plugging in the values. And because now we're even in 3 variables, we hope that the limit actually does not exist, because we'd have to try to prove it using epsilon and delta. So the idea here, I think, is the limit will not exist, and it's up to you to try to figure out what paths to take. I suppose you can just enter D and E and then you'd be done without doing any work, but that's not going to fly on the test. So let's figure out what kind of paths to put in there. And then we could try combinations of x and x equals 0 and y equals 0 and z is equal to 0. And those would be like paths going along an axis, the x-axis, the y-axis, or the z-axis, because now we're in 3 dimensions. And let me just do one of those. So paths that we're looking for, let's try x equals 0. So we're having, I think we have to do 2 at a time, because then this will be a 3 variables. X and y are equal to 0. And we have the limit as z approaches 0. So x and y is equal to 0, and 0, 0. And again, before we take the limit, we simplify this expression to be 0 over z squared, which is equal to 0. And so that's not, that's going to give us one path that's going to give us the same thing. X equals y equals z squared. So now let's try this path, x equals y. And maybe we should do another path that might give us 0 again before we do this. Oh, let's try this one. So if we change everything into z's maybe, and then so wherever we see an x, we'll change that into z squared. Wherever we see a y, we'll change that to z squared. So we'll take the limit, and so in effect, we'll get rid of the x and the y variables. And so wherever we see an x, we'll put a z squared. Wherever we see a y, we'll put a z squared. So wherever we see a y, we'll put a z squared, and this is just a z squared. 2, wherever we see an x, we put a z squared, and this is a z squared. Z squared squared plus z squared squared plus z to the 4th. So everything that's in parentheses here was once an x or a y. And you can figure out which was x and which was y, but it doesn't matter because we're going to call it z squared. And then we'll see up in the numerator, we're going to have z to the 4th, and there's 1, 5, plus 2 is 7. Did I add right? Yeah. Okay. And then here there's z to the 4th, z to the 4th, z to the 4th, so this is 3z to the 4th. 7/3. Which is not equal to 0. Yeah, I wanted to try a different one first, like x equals y equals z, and then see what happens there. Kind of blew the punchline for us, but it's all right. So how did you figure, Evan? How did you figure x equals y equals z squared? Because that was kind of like Joe's question earlier.
Because it's kind of like the reasoning we used on the previous one. It's on the bottom you have x squared plus y squared equals z to the 4th, which is z squared squared. And on the top you see it's all powered through. It's all
Well, I think you're on the right track. So it's all on top. It's all like z squared. There's z squared and then with an x, and there's z squared with a y. So it seems like we're trying to match this power down here, z to the 4th. And so it seems like we might want to move towards getting everything in terms of z to the fourth, or getting everything to look like z to the fourth. And with this replacement of letting x equal to z to the fourth and letting y equal, or letting x equal z squared and letting y equal z squared, when you multiply it up on top, you get z to the fourth, and that's exactly what was happening here. And so try to match it up with the denominator so you can easily cancel. And hopefully not, because this was equal to 0, our idea is to not come up with a 0 for our answer. And I think this is the best way to do it. And my other idea, had you gone this way, not squared, but if you just said x equals y equals z, and then plug in those values, then I think this is still going to be equal to 0. So limit, won't go all through the work here. Whatever. It's going to go to 0, which would have matched our first one, our first obvious one. So this wouldn't have gotten us anywhere. So there's going to be some times where you might have to try 2, 3 different paths before you get to the correct one. Okay, hopefully not more than that in a test situation, because you'd be running out of time. Okay. Any questions? All right, so this is a 3D or a 3 variable example. Now let's get to the other thing. Partial derivatives. I don't know if I want that agenda. Maybe I should just tell you what the derivatives are. So let's take a look at a function. Some random function. What we want to do is, the definition of partial derivative is to take the derivative with respect to, in different parts, with respect to one variable. So we know from calculus that if we have a function and we say df dx, and then we take the derivative of that function, and we denote it, we say we're taking the derivative with respect to x. So we say f prime, but you'll see that this Leibniz notation will come a little bit more importantly for us, because this is going to tell us that we're taking the derivative with respect to what variable. Now that we have two different variables, we have to be a little bit more careful about using Leibniz notation and to actually say what we're taking the derivative with respect to. So they have this whole thing where, if you remember, the derivative f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. And it's the same idea here, except again we're dealing with two variables. So let's see if we can approach this derivative. You know what WRT stands for? With respect to? So the derivative with respect to x, by definition, we say this is equal to limit as h approaches 0, so the same h, Now, in this function, what we're going to do is we're going to offset the x. Remember, there's two variables here, so we need to keep track of the y as well. But what we're going to do is we're not going to do anything with the y, because we're just going to be focused on the x. So we're going to do the offset along the y, and then we'll have this get closer and closer to the secant line gets closer and closer to the tangent line. And so we have this derivative notation, or this is a definition. Okay? Now, unfortunately, I'm going to erase this. I mean, if you want to scratch it out, and you write it and scratch it out, that's fine. But I'm not. Unfortunately, we can't use this definition or this notation anymore because the d over there stands for like a derivative, and in math it actually means the total derivative or the big derivative. And so if whenever we're dealing with partial derivative, we need to change our notation a little bit for the d. So instead of this d, we're going to use another symbol. And the symbol kind of looks like a d, but it's not a d. And it's not a Greek letter either. It's just a weird symbol. And so sometimes this is known as the partial symbol, a partial of f with respect to x. So that's our formal definition, and the other definition is the partial of f with respect to y is going to be equal to essentially the same thing, and you can see the difference as I write it here. We have f of x, comma, now the offset is happening in the y component, minus f of xy all over h. So this is the partial of f with respect to y. Now there is a slightly nicer way of expressing this derivative. And sometimes, and the book does this a lot, sometimes they use a subscript of the variable that you're taking the derivative with respect to.
It's really confusing that the associated with the homework doesn't do it.
Yeah, well, there's no prime. That's the other important thing. We don't use prime anymore, like f prime that we did back then. We can't use prime anymore because prime doesn't signify. Prime assumes that there's one variable and you know the derivative we're taking them with respect to. And unfortunately here, because we have a function of more than one variable, we have to specify exactly. And so because we're taking the derivative already, this subscript says derivative, and so it's kind of like redundant to put the prime there. So in our example, really simple example, the thing to do is that if you have that function x squared plus y to the fourth, that if you're taking the derivative of that, what you're going to do is you're going to take the derivative of x with respect to x, and you're going to pretend that y is constant, because that's exactly what's happening. You're not moving y, so you're going to fix y to be constant. So this is your answer, or more specifically, you can say plus 0 because y to the 4th power is a constant number. And so f sub y is going to equal to the derivative of 2x with respect to y is a constant. So you just have 4y to the 3rd. Okay? So that's, the shortcut way of doing the derivatives. And the idea is to treat the other variable as if it was constant. So let's do a couple more quick derivatives. So with respect to x, if we're taking the derivative with respect to x, this is a variable. This is all constant with respect to x. And this is the other variable. So I'm going to have 0 for the middle term. Now I'll take the derivative of 3y is a constant times x. So pretend y is like 5. So 15x, derivative is 15. So the derivative of this is just going to be 3y, and then x is your variable, and then I'll put a 0 there to say that derivative there is equal to 0, and then this is going to be 2z. Okay? You guys get the hang of it? So treat the other variables, although they are variables, you have to treat them as if they were constants. So in your head, you could pretend that they're like equal to 2 or 5 or something. And then go ahead and look for the derivative, the variable you're taking the derivative with respect to, and then that's going to be your only variable, and that's what you're going to treat as a variable. All right? So what we'll do next time is we'll dive into a little bit of geometry of this for functions of 2 variables. We'll take a look at more examples of just taking quick derivatives, and then we'll see how this will relate to a tangent plane. John? Yeah. Yeah.
That's kind of weird. We'll talk about that later.
I
thought it was you take the
well, this is something we could talk about next time. But you guys are going to do it in your lab, so by the time you come next time, then you'll know.
Well, I worked on it. I'm not sure.
Yeah, this is the second derivative, so the order is important of what you take the derivative with respect to. Oh, unfortunately, Leibniz notation is backwards. Good luck with that.